Welcome to the matrix keypad. A matrix keypad provides a large number of input switches while requiring a low pin count. If individual input switches were used, then each switch would require its own input pin on the microcontroller. For example, if 16 input switches were needed, then 16 microprocessor input pins would be required. A multiplex keypad provides a large number of switches but a much lower I/O pin requirement from the microprocessor than individual switches would. Let's take for example the picture that we have here shown, and this is a 16 switch keypad. Let's assume though that this is a non-multiplexed. For a non-multiplex type of keypad, we would require a pin for every switch on there. And by pin I mean on the microcontroller, on the microprocessor. So therefore we have 16 switches, so therefore we would need to have 16 input pins available on the microcontroller. Now the other thing also is that the other side of the switch is connected to a common pin. So on the back of the keypad you would find a total of 17 pins. Now for example, if you had a 5x5 for example, so a 5x5 would require, or would have I should say, 25 switches, and therefore would require a total of 25 input pins on the microcontroller. And you also have to have a common pin on the back of the keypad, so therefore you would have a total of 26. Right now, where a matrix keypad comes into play is that it saves you on the I/O pin requirement. So the arrangement is really that you're going to have a pin for each row and a pin for each column. So here we have a diagram of the underlines of a matrix keypad. A matrix keypad is also called a multiplex keypad. And so as you can see in the diagram, you have a pin for each column and a pin for each row. So for this 4x4 multiplex keypad, the pin requirement is only 8. If I had a 5x5, the pin requirement would be only 10 pins. So when you compare a multiplex keypad with one that is non-multiplex, you can see that a multiplex keypad definitely saves you on the I/O pin count, because again, all you need to have is enough pins for all the rows and all the columns. So for example, if you ran up to an 8x8, well, if you had a non-multiplex keypad, an 8x8 would require to have 64 input lines, and also on the back of the keypad you would have one more pin that would be a common pin. So you'd be up to 65 pins on the back of the keypad. But if it is a matrix keypad or a multiplex keypad, therefore the pin requirement drops down to only needing 16 input pins on the microprocessor. So again, there's another example as to why going this route can definitely save you on the requirements on the microprocessor itself. Now it states here, this arrangement requires just 8 circuit connections to read the states of 16 switches. Other arrangements are also available, such as the 12 key, which is a 4x3 keypad. This keypad requires only 7 circuit connections. The 25 key, which is a 5x5 keypad, requires only 10 circuit connections to read the states of 25 switches. Rows and column numbers are arbitrary and vary from one keypad manufacturer to another. The keypad's electrical circuit contains no active electrical components. It is simply a matrix of column wires and row wires. When a key is pressed, the corresponding column wire and row wire make contact. So in a sense, when you're pressing a key, you are shorting a column wire and a row wire together. When the key is released, the corresponding column wire and row wire go back to an open condition. To detect a pressed key, the microprocessor must scan the keypad to look for a short circuit condition. If a short is detected, the microprocessor must determine which row and column wires are connected to identify the pressed key. One way to scan a matrix keypad is to hold the row and column wires at some voltage and then drive one of the row wires to a different voltage. If one of the keys is pressed, the corresponding column wire will be shorted to the row wire, thus changing the voltage of the column wire from the V1 voltage to the V2. The key that was pressed can be determined by knowing which row wire was driven at the second voltage at V2 and which column wire changed to V2. Here we have the microprocessor interfacing scheme. Now the following is a diagram of a 4x4 matrix keypad interface to a 68AC11 using port C. PC0 through PC3 are configured as output pins, while PC4 through PC7 are configured as input pins. Looking at the diagram a little bit closer, we can see that each of the column pins is being pulled up with a 47 k ohm resistor to VCC. We'll let VCC be 5 volts in this case. But the sampling is occurring where you see PC4, PC5, PC6, PC7. We're also going to be sending out from the microcontroller values that are going to be seen at the rows. So the lower nibble of port C will be configured as outputs, and the upper nibble of port C will be configured as inputs. Let's take a look at how we would scan the keypad in order to see which button has been pressed. One of the things that port C will do is to be placing values on the rows. Remember that PC0 through PC3 will be configured as outputs, and then PC4 through PC7 as inputs from the perspective of the microcontroller. So as an example here, what the microcontroller will do is to place row 4 as a low and everything else as a high, and then it will sample what is happening at PC4, PC5, PC6, and PC7. It will sample that. Now, if the first button has been pressed, for example, if we were to have pressed this button right there, well, what that would cause is this particular point, which is connected to PC7, to become a low, and everything else will remain a high. Now, if the second button was pressed, then we would have a low at PC6, and all the other pins would be highs right there as far as PC4, PC5, and PC7. If this button was pressed, that would place a low at PC5, and all the other inputs would be highs. And then finally, if we were to push this last button on this row, on row 4, we would get a low at PC4, and it would be highs on the other inputs. Now, what is happening here is that we are placing a low on row 4, and therefore we're sampling to see if any of the buttons on that row have been pressed. And therefore, when the button is pressed, it's going to short out that particular input pin to ground, because having a low, right here, having a low on PC0 is like basically shorting it to ground, so therefore it'll register as a logic low, as you can see. So if this last button is being pressed, you can see that we have a logic low on PC4, and all the other inputs, PC5, PC6, and PC7, will be highs. Now, if a button has not been pressed on row 4, well then we will be sending out a 0 to PC1 and making PC0 a high. And so now we'll take another sample. We'll take a reading of PC4 through PC7 and see if any of the buttons has been pressed. Now again, if the first button has been pressed here on that row, then we'll get a low at PC7, and we will see highs on all the other pins. If the second button has been pressed, we'll see a low at PC6, and we'll see highs at the other inputs. If that's not the case, say for example this button was pressed, well, that would cause the PC5 input pin to go low, and all the other pins would stay high. And if the last button was pressed, then it would cause PC4 to go low and all the other inputs to be high. Well, if nothing on that row was pressed, well, we continue on and we make the next row become a low. So now we have a low here and all the other rows are high. So again, if a button on that particular row, on row 2, is pressed, it will register as a low on PC4 through PC7. One of those will be low. An example is, say if I was to have pressed this button here, this would become a low and the rest would be highs. And again, if a button is pressed in the code, we would tell it to basically branch to somewhere to make it do something. Maybe we could have it turn on an LED, for example, but there would be a response to a button being pressed. And finally, if nothing had been pressed on that particular row, next what we would do is to make row 1 low, and therefore again we would take a reading of PC4 through PC7 and see if one of the buttons there has been pressed. Let's say this last one has been pressed, or is being pressed I should say. Therefore this would go low and everything else would be a high. So that's how we're able to scan. Now once we finish as far as with row 1, and if nothing has been pressed, then we basically start it all over again. We would go back with a 0 back to PC0 and start the sequence all over again. So basically we're passing a 0 from row to row to row until we're able to sense that a key or a button has been pressed. Well, let's think about some code and see how we can come up with something that would work for this 4x4 keypad. So one of the first things, as we've seen from previous labs, is that we have to have an origin. So let me go ahead and write that down. We have org $, and we're going to start it off at F800. Let's start it off at F800. And the reason we're starting this off is because it is the start of EEPROM for the 68HC11E2 chip. That's the one which we are emulating. That's the one that we are following in our class. So we started at F800. The next thing we do is we need to initialize the stack. So let's go ahead and take care of that. So we have an LDS, and we're going to put a value into the stack. And let's start it off at 0, 0. And really we could start at 0, 0 FF, and it shouldn't have a problem at all. So let's go ahead and do that right now. Let's start at 0, 0 FF. That would place it at the very top of RAM, so therefore we have all of RAM to use for the stack. So therefore, if you recall that the CPU uses the stack in the performance of its operation, so it's something that it definitely needs to have. And the best thing to do is to initialize the stack so that you have a good starting point, and that will take care of having enough room for the CPU to use in the performance of its operations, as stated earlier. Alright, so the very next thing we need to do is we need to configure port C. Remember that PC4 through PC7 is going to be used as inputs, and PC0 through PC3 is going to be used as outputs. So we need to configure the Ddr C. So therefore I'm going to load accumulator A with a value. Now again, the upper nibble is going to be inputs and the lower nibble is going to be outputs. So therefore I'm going to load a 0F and I'm going to store that at the Ddr C, which is 1007. And so that takes care of the Ddr C. That makes the upper nibble to be inputs and the lower nibble to be outputs of port C. Now, after we do this, we can then send a value to make row 4 a low and make all the other rows highs. Now, the other thing also to consider is, well, we're still going to have to send it a full byte, all right? We're going to have to send it 8 bits. But the thing is, if we configure PC4 to PC7 as inputs, we could pretty much send it anything, and it's just going to ignore it because those pins have been configured as inputs. But just to keep things straight, I would say the best, if you were to argue between sending lows and highs, I would say just to keep it straight. For example, in my head, and that's probably the best way of stating it, and since each of those inputs is being pulled high, why don't we just say that we're going to go ahead and send highs to them, even though it doesn't really matter if I send highs or lows, because it's going to be ignored, because those pins, PC4 through PC7, are configured as inputs. So whatever I send to it is just ignored anyway. But just for our sake, we still have to per se send something to it, even though it will be ignored, because we have to send a full byte to port C. So I'm going to load accumulator A with this value here, where it's going to make PC4 through PC7 all highs, and it's going to give me the row values indicated here. All right. So therefore, I'm going to send it an FE value. All right. Now the next thing is, once I send it that, I have set row 4 low. I've set it a low. So now if I take a reading, and if a button is being pressed on row 4, I will see one of the upper nibble bits actually be a low, and so therefore I know that something has been pressed on row 4. Right? So what I'm going to do then is, of course, take a reading. So I'm going to store, actually that's not the next line of instruction. I loaded accumulator A, but I still need to, actually that is the next line instruction. I need to store it first, right? I loaded accumulator A with a FE, now I need to store it. I need to store it where? Well, I need to store it at port C, so that's going to be 1003. That's port C right there. So now that port C is loaded, I'm going to take a reading of it. So this is load accumulator A with the contents of address 1003. So when I load accumulator A with the contents of port C, I'm taking a reading of port C. So I'm doing a read right here. Now after I do a read, here's a thing that is pretty cool, is that I'm going to do an ANDing. I'm going to do an ANDing of whatever value I have received from port C, because I want to ignore what's happening at PC0 through PC3. Regardless what value I sent out, when I take a reading of it, I really only care about PC4 through PC7. So I want to make PC0 through PC3 always come out to be the same value. So what I'm going to do is I'm going to do an AND A. I took a reading of port C and loaded it into accumulator A, but now I'm going to do an ANDing of A. And I'm going to AND A with the value of F0. So by doing an ANDing, I'm basically ignoring what's happening at PC0 through PC3 and forcing them to always be low. It's not changing what the status is of those pins. It's just when I took a reading of it, I really don't care what was read at PC0 to PC3, so I am forcing them to become low. Therefore, it makes the values that I compare against a whole lot easier. Now, to give you an example, say if I took a reading of port C, and right now I have something like this. I'll have PC7 be a 1, PC6 a 1, PC5 be a 1, and let's say that I had pressed this button here. PC4 will be a low, and PC3 is a high, PC2 is a high, and PC1 is a high, and then PC0 is a low. So as I stated, I'm going to AND it with an F0. So I'm going to AND with a 1, 1, 1, 1, and a 0 here. So therefore, what I'm going to do is, if I AND this 1 with this 1, I end up with a 1. And if I AND this one with a 1, I still end up with a 1. And if I AND this one with a 1, I end up with a 1. And if I AND this 0 with a 1, I end up with a 0. So you can see that everything on the upper nibble of port C was passed through. Now what I want to do is I want to force the lower nibble to be all lows. So a 1 ANDed with a 0 is a 0. A 1 ANDed with a 0 is a 0. A 1 ANDed with a 0 is a 0. And a 0 ANDed with a 0 is a 0. So I'm forcing the lower nibble to always be a low. That way it makes whatever values I will compare against to be the absolutely lowest number of them. Now, with that stated, let me go back. What we need to figure out at this point is what are the values that I will be comparing against? Well, to provide a heads up here, okay, I will have to compare, okay, what is in accumulator A against a value for each column. Since I have 4 column wires, okay, since I have 4 columns, I'm going to have to compare against 4 values. So let's just say that if I had pressed this button right here, okay, that would have given me a 0, 1, 1, 1. Well, after the ANDing, okay, the value that I would see if I'm ANDing what was received from port C against an F0, then the value that I would see if this button is pressed is going to be a 70 hex. Now, if the next button had been pressed, if this button had been pressed, of course, some of the values here will change. This will change, this will change. This would be a high then, and this would be a low then. Okay, again, only the second button is being pressed now, okay? But I need to figure out what the value is that I'm going to be looking for. Well, at PC4, I have a 1, PC5 I have a 1, PC6 a 0, and PC7 I have a 1. And again, the lower nibble will be all lows because of the ANDing. So therefore, when you look at what's the value total, well, it would be 1, 0, 1, 1, 0, 0, 0, 0. But this provides you a what? That's an 8 and a 2, and an A, then a 1, so that's a B0. So I would have to be comparing against a B0 hex. Now, if the third button had been pressed, well, then I would have a 0 here, and this, since it's not being pressed, would be a high. So the value here would be a what? Well, again, we have a 1, 1, 0, 1. Those are the values for the upper nibble, and the lower one is being forced to always be a low, so therefore we would have a D0. So this would be a D0 hex. And if the last button was being pressed, right here, okay, that would force this one to go low and everything else be a high. Again, the last button is the only one being pressed, so therefore I would have a 1, 1, 1, 0 in the upper nibble, and the lower nibble, of course, is being forced to be lows because of the ANDing that I have right here, and so therefore I'm going to be looking at a E0 hex. So that's the value that I'm going to be comparing against, an E0 hex right there. So to continue on with our code, let's just say that we're going to start the comparison. After we AND it, we can really just jump right into it and start comparing. So I'm going to do a compare accumulator A against the value of 70 hex. Now I'm trying to see if that first button on row 4 has been pressed. Well, if it has been pressed, okay, now when you do a comparison, what's happening here is that the CPU is going to subtract what's in accumulator A, okay, and the value that is after the compare instruction itself, which in this case is a 70 hex. So really it's going to do a subtraction of those two values. Now the one thing that's important here is that if they are equal, the result is going to be 0, and if it's 0, then the Z flag will go high. And if the Z flag goes high, that's how it knows to branch. So therefore, we're going to use a branch if equal instruction here. Branch if equal, BQ. That basically says if the two values are equal to each other, branch. Okay, so where's it going to branch to? Well, let's provide some sort of assignment to the keys themselves. Let's say that the keys have values, and let's say that the values, that if you were to press this key here, it's a number 1. This key is a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, and this would be like an A, a B, a C, this would be a D, an E, this would be the F, and this would be, for example, a 0. So if that was the case, let's just say that if a button was pressed, that we would basically send a value to port B to give us that value in binary. All right. So for example, then, if we're on the first row, and if we do see that a 70 is actually being sampled from port C after the ANDing, therefore we're going to tell it to branch, right? So branch if equal to what? Well, let's just call this particular label LED 1. So somewhere at the end of the program we have LED 1 that is going to turn on the binary value for a number 1 at port B. Now, if they're not equal to each other, it's just going to continue on to the next line. So let's go ahead and compare again. We're going to tell it to compare A, but this time we're going to compare to see if the second switch has been pressed, which will be a B0. So we're comparing A against a B0 now. Now again, if it is a B0, branch if equal, and let's tell it to go to LED 2. Now LED 2 is going to send to port B the binary value that is going to be the number 2. Well, if that button has not been pressed, we keep on. We're going to do another comparison. So we're going to tell it to compare A against the value D0. And again, if that button has been pressed, those two values will be subtracted from each other, right? But the answer or the result will be a 0, causing the Z flag to go high, and the branch if equal statement or instruction is hinged on the Z flag. So therefore, if it is equal, by using this instruction BQ, it's going to branch. And we'll tell it to branch to LED 3. And again, we have some code somewhere else at the bottom of the program that's going to turn on port B with the binary value of 3. Okay, hopefully that's already understood. Okay, and that's pretty much what will happen is when we branch. Okay, so let's continue. Next thing is to compare. Again, we're going to compare A next with a value of E0. Okay, E0. So at this point, if it is equal, okay, that button is being pressed, therefore we're going to tell it to branch if equal to LED, and that's going to be LED 4. And perhaps I should have done that in orange. So LED 4, just so it stands out a bit. Okay, now what happens if nothing has been pressed? Well, if nothing has been pressed, then we need to go ahead and now we need to change row 3 to a low and change row 4 to a high. Again, we're having to shift the low on the rows. So now, in a sense, what we're doing is repeating the same code, except we're going to send a different row low. So therefore, what we have is something like this, and I'm just going to start it off here. And this arrow basically means that after this last statement of BQ LED 4, we're going to go ahead and have some more code. I don't have enough space to keep on here, but I'm going to put it on the side right here. But we would again do this. We would load accumulator A, so LDA, and in a sense it's following kind of what the structure is, okay, on the first column of code right here. And we're going to send it a value, but what's this value that we're going to send? Well, we have to go ahead and make PC1 a low, so therefore we're going to send it an F, and there's going to be D, because PC3 is high, PC2 is high, PC1 is low, and PC0 is a high. So that would be an FD. So we'd send an FD. Now again, we'd basically store that at port C, so 1003. Then we would load accumulator A, because we're going to take a reading of port C now to see if anything has been pressed on that second row. Well, by second row I mean row 3. Okay, so we're checking to see if anything on row 3 has been pressed. Now again, we're going to have to AND it. So we're going to do an AND A against an F0. And then we're going to do a comparison again. And again, it's the same values we'll be using. We're going to compare A against a 70. The thing is, we know that we're on the second row right here. Because why? And again, by second row I mean row 3. But why? Because we placed row 3 low. So now we can go ahead and say, well, if it is equal to 70, branch of equal, right? If that button has been pressed. And we're going to tell it to go this time to LED 5. Branch of equal to LED 5. And perhaps changing the color would help. So LED 5. Now, if that button has not been pressed, well, we compare again. Compare A against the value of B0. And if it is equal, branch of equal, well, this time we're going to branch to LED 6. And again, we have some code further on down that turns on that particular binary value at port B. Now, if that button has not been pressed, let's go ahead and go on to the next comparison. So we're going to compare A again against an E0. Actually, this is D0. Alright, so we're going to compare A against a D0. And if it is equal, we're going to branch if equal, a BEQ, and we're going to go to LED 7. Now, if that button 7 has not been pressed, well, we're going to compare again. We're going to compare A. Excuse me a second, let me erase this. We're going to compare A against an E0, and if it is equal, branch of equal to LED 8. Now again, if none of those has been pressed on that row 3, we're going to tell it to go ahead and continue on, but we're going to have to change it so that the row that row 2 is low. So let's go ahead and do that. So row 2 is now made low, and row 3 is gone high. So we're going to have to load a value. So we're going to load accumulator A with, in this case, it's going to be an F, and that's going to be an FB, because we have a high on PC3, a low on PC2, a high both on PC1 and PC0. So that would be a B right there. So we're going to load it with an FB, and we're going to store accumulator A at 1003, and then we're going to load accumulator A with the contents of port C. Then we're going to AND it again with an F0, and then we're going to start our comparisons. We're going to compare A against a 70, and if it is equal, we're going to tell it to jump to LED 9, because that first button on the left on row 2 is being pressed. All right, so if it's being pressed, it's going to be equal. Our Z flag will go high, and therefore it's going to branch. So branch of equal to LED 9. Again, Everything in the orange, these are labels, and we're going to have some code here after what I'm putting up on the screen that basically again provides the binary value for that particular key to be sent out to port B. Again, to port B. Alright, so if that button has not been pressed, well, let's compare A against the next value, and which is a B0. And if it is equal, branch of equal to LED 10. Well, in this case, it'd be LED A. LED A. Well, if nothing has been pressed, okay, so far, then keep on comparing. Compare A against a D0. And if it is equal, branch to, in this case, it'd be LED B. Well, if nothing has been pressed yet, then go on comparing. Compare A against an E0. This is a dollar sign right there. Against an E0. And if it is equal, branch of equal to an LED C. Well, if nothing on that row 2 has been pressed, well, we're going to have to now change the low on the row. Okay, so therefore we need to come back over here and change this row 1 to a low, and row 2 has become now a high. Okay, I changed the color on that. Now as far as code wise, well, we have to take care of the last row. So therefore, continuing on with the code, we're going to load accumulator A with the value of F. And what is the value? Well, if you look at what's happening at PC3 through PC0, we see that we're sending a 7. So it'd be a 7F that we're sending there, 7F. And then we're going to store accumulator A at 1003. And then we're going to load accumulator A with the contents of port C, which is at address 1003 again. Then we're going to AND A with an F0. Then we're going to compare A against a 70. Again, is that first push button, or the first button on that row, being pressed? If it is, we're going to branch till it be Q, and we're going to branch to LED D. So LED D, for example. If that button has not been pressed, well, we're just going to keep on comparing then. Compare A against the value B0. If it is equal, branch of equal then, to LED E. If that button has not been pressed, keep on comparing. We're going to compare A against the value of D0. If that button has been pressed, we're going to tell it to branch of equal to, and that's going to be LED F. Now, if that button has not been pressed, we will continue. For our last comparison, compare A against the value of E0, and we're going to branch of equal to LED 0. Okay, LED 0. Now, after we did all the comparisons here, if nothing has been pressed, then possibly we should just have a jump instruction, a jump, and we'll call it to jump back to possibly something like over. Okay, jump to over. And so therefore the over really needs to start with the sending out of the rows again, making row 4 low again. So really, I should probably put the label OVR right here. Okay, and so that would start the program over. Now down here, okay, we would have all of the labels that are in orange, that LED 1, LED 2, LED 3, we would have that, and the associated code to turn on the binary value for that LED at port B. And I think that that's fairly straightforward, so I will abstain from showing that here, especially since I am running out of room. So the objective of the microprocessor is to continuously go from row to row, making one of them low while maintaining the rest high, and checking the status of the columns after each row change. To sense a specific key being pressed, the microprocessor must have the corresponding row low and sense a low on the corresponding column. The microprocessor can then execute programming associated with that particular key. In the exercise procedure, we have the following diagram for the Ddr Sim 11 keypad. So this shows how the column wires and the row wires are connected in the simulator. So we have the column wires, column 1, column 2, column 3, and column 1 is connected to PC4, column 2 to PC5, and column 3 to PC6. As far as the rows, we have row 0 connected to PC0, row 1 to PC1, row 2 to PC2, and row 3 to PC3. So again, this is the configuration by default for the keypad in Ddr Sim 11. Now, towards here in the bottom, one of the questions that needs to be solved for is, what is the value that you're going to send to the Ddr C? Based on the example which was provided, okay, use the same process to figure out what is the value that you would send to the Ddr C. Now, one of the things is, as a hint, is that we're still going to have PC6, PC5, and PC4 as inputs, and PC0 through PC4 as outputs. And really, PC7, well, do you really care if it's an input or an output? Because it's not going to actually be used at all. So you could possibly just use the same value that was in the example, where you took all of the upper nibble of port C as inputs and the lower nibble as outputs. Now for part 2, to check if a button has changed state, meaning pressed, a reading of port C is made. To isolate bits PC4, PC5, and PC6, the value read from port C will need to undergo an AND operation against the value of what hex. Now, what we need to do here is to again pay attention to what is it that we want to see. Well, we really want to see just the values at PC4, PC5, and PC6. Okay, so we need to let those values pass through. Okay, so in the ANDing, those particular bits in the AND value, those particular bits need to be high, and all the other values in the AND value need to be low. So therefore, with that information, with that hint right there, you should be able to come up with the AND value that you'll be using against possibly accumulator A or maybe even B, whichever one you choose to use, of course, in your code. But again, what is the AND value itself? Because we're going to have to do an ANDing, and we want to isolate or allow to pass through what is in PC4 and through PC6 and block everything else. Now, as far as step number 3, we also have to figure out is really what are the values that we're going to be comparing against. Okay, if we're on a button on column 1, for example, or a button on column 2 or column 3, what is the value that we're going to be comparing against? Again, every column has to have a value, just like in the example. So what you need to do is to give this some thought and come up as to the value that you would be comparing against after the ANDing. Okay, after the ANDing. So once you take a reading of port C and then you AND it, then what are the values that you're going to be comparing against? Now once you have figured that, you're to use Ddr Sim 11 to write and verify a program that displays the binary representation of the key being pressed on 4 LEDs which are connected to PB0 through PB3 respectively. In other words, when you press a key, whatever value is on the key, like a number 4 or a number 8, what's supposed to happen is that the binary value of that number is to show up on port B. Now the other thing also is that the program should view the asterisk key as a number 10 and the crosshatch key on the keypad as a number 11. And then the last thing, of course, is once you have your program up and running, make sure that you show this to me. And for the course that's 100% online, definitely take a picture, as you've done on all the other labs, and upload that onto Blackboard of your code that has been verified to work. Thank you.